Hello everyone, welcome to this session. In this session, we are going to study transforms, Fourier transform, Fourier cosine transform and Fourier sine transform. In our previous session, we discussed Fourier integral, Fourier cosine integral and Fourier sine integral, and we solved some examples on Fourier integrals. Now, in this session, we will see Fourier transform. So to define Fourier transform, first we have to understand complex form of Fourier integral. So first we look at complex form of Fourier integral. Then we discuss Fourier transform and inverse Fourier transform, and Fourier cosine transform, inverse Fourier cosine transform, and Fourier sine transform, inverse Fourier sine transform. And we solve some examples on Fourier transforms. Now let us see what is complex form of Fourier integral first. So here complex form of Fourier integral is fx equal to 1 by 2 pi minus infinity to plus infinity. Here 1 by 2 pi integral minus infinity to plus infinity, integral minus infinity to plus infinity f of t e power I lambda into t minus x dt d lambda. Here we prove this complex form of Fourier transform. We prove this complex form of Fourier transform using Fourier integral formula. So Fourier integral formula is fx equal to 1 by pi integral 0 to infinity, integral minus infinity to infinity f of t cos lambda into t minus x dt d lambda. Now here from this definition of integration, Fourier integral, we can derive Fourier transform, but before that here we use one definite integration formula. That formula is integral minus a to a fx dx equal to 2 integral 0 to a fx dx if this function is even, and this integral is 0 if this function is odd. We use this definite integration formula here in deriving this complex form of Fourier integral. So now let us see, we can write this integral as here cos lambda into t minus x. Either integral is minus 0 to infinity, right? So this can be integral 0 to infinity cos lambda into t minus x d lambda can be written as integral minus infinity to infinity 1 by 2 integral minus infinity to infinity cos lambda into t minus x dt d lambda. How means? First we use this formula. Using this definite integration formula, here we can write integral 0 to a. If function is even, we have seen integral minus a to a fx dx equal to 2 integral 0 to a fx dx. If you transpose this 2 to left hand side, we get integral 0 to a fx dx equal to 1 by 2 integral minus a to a fx dx. Here we use this when function is even, we can write this integral in this form, and we use this formula to modify this integral cos lambda into t minus x d lambda. Now here this cos lambda into t minus x cos lambda into t minus x is even function. How even function? Here cos of minus theta equal to cos theta, we know this one. That's why this function cos lambda into t minus x can be written as cos of minus lambda into t minus x. Here that means if you replace lambda by minus lambda, here we get cos minus lambda into t minus x, but according to this formula, this is equal to cos lambda into t minus x. That means cos lambda into t minus x is even function. If this is even function, we can apply this definite integration formula. So according to this formula, we can write integral 0 to infinity cos lambda into t minus x d lambda equal to 1 by 2 integral minus infinity to infinity cos lambda into t minus x d lambda. So we replace integral 0 to infinity cos lambda into t minus x d lambda using this. So when you replace that, we get 1 by pi integral 0 to infinity, integral minus infinity to infinity, f of t cos lambda into t minus x dt d lambda equal to, in the place of integral 0 to infinity, here we will have integral minus infinity to infinity according to this, and here 1 by 2 is there, that's why here 1 by 2 pi, integral minus infinity to infinity, integral minus infinity to infinity, remaining terms no change, that means f of t is there, so here f of t as it is, dt as it is. So f of t cos lambda into t minus x dt d lambda. Now here after modifying this using a definite integration formula, here we can write this as 1 by 2 pi integral minus infinity to infinity, integral minus infinity to infinity f of t cos lambda into t minus x dt d lambda. Let us say this is equation 1. Now let us see cos term. Here if this cos lambda into t minus x is even, then we can understand this sine term. Here sine function is odd function. So if we consider sine instead of cos, then sine lambda into t minus x is odd in terms of lambda. That means if you replace lambda by minus lambda in sine lambda into t minus x, then sine minus lambda into t minus x gives minus sine lambda into t minus x, which is odd because here f of minus t equal to minus of f of t. This is definition of odd function. So here according to this sine function is odd. So sine lambda into t minus x is odd function. If this is odd function, then according to definite integration formula, integral minus infinity to infinity sine lambda into t minus x d lambda equal to 0, because we know integral minus a to a fx dx equal to 0 when fx is odd. So according to that definite integration formula, here this integral is 0. If this integral is 0, then if you multiply this integral or this integrand sine term by any term, if you divide this sine term by any term except 0, then that will be equal to 0. So here we multiplied this sine term by f of t and 1 by 2 pi, then we integrated this again with respect to t. Here this is integration with respect to lambda. So here in this step we have multiplied this sine term by 1 by 2 pi f of t, and we have integrated again with respect to t under the limits minus infinity to infinity. Still this LHS becomes 0 because this integral sine term is 0. Okay. Now here we can write this in reverse manner. 0 equal to, it means here I have written RHS first, LHS next. Let us say this is equation 2. Now let us multiply this equation 2 by I, then let us add this to equation 1. So here if you multiply equation 2 by I and add to equation 1, then we get on left hand side f of x plus 0 equal to, here RHS of equation 1 by 2 pi integral minus infinity to infinity, integral minus infinity to infinity f of t cos lambda into t minus x dt d lambda plus I into RHS of equation 2. So I into 1 by 2 pi integral minus infinity to infinity, integral minus infinity to infinity f of t sine lambda into t minus x dt d lambda. Now in both these integrals 1 by 2 pi is same and these integrals are same, and here also independent variables, that means dt d lambda is same and f of t is also same. So if we take all these similar terms common, then we can write this summation, this sum as 1 by 2 pi integral minus infinity to infinity, integral minus infinity to infinity f of t. We have taken all these terms common, then within the bracket we get cos lambda into t minus x plus I sin lambda into t minus x dt d lambda. Now here we apply this formula here. Here cos theta plus I sin theta equal to e power I theta. So here if you observe this, in the place of theta, here it is lambda into t minus x. So we can write this cos plus I sin term using this formula, Euler's formula, as 1 by 2 pi integral minus infinity to infinity integral minus infinity to infinity f of t. All these terms are same, no change. Instead of this cos plus I sine, we can write e power I lambda into t minus x dt d lambda according to this Euler's formula. Now this is nothing but complex form of Fourier integral. Now here you can split this exponential term. You can write this exponential term as e power I lambda t into e power minus I lambda x dt d lambda, means remaining integrals are same. Now if you take this e power minus I lambda x outside, and if you consider all t terms inside, that means f of t dt and one integral, if we write inside this square bracket, we get 1 by 2 pi integral minus infinity to infinity e power minus I lambda x, then integral minus infinity to infinity f of t e power I lambda t dt, and we have written d lambda outside. Now this term which is in the bracket is nothing but f of s. What is f of s? F of s is nothing but Fourier transform. So let us see. We have written complex form of Fourier integral, or complex Fourier integral is this one. We have seen this derivation. Now in this derivation, the term which is in the bracket here, this bracket, is nothing but Fourier transform. Here this is in terms of lambda, and here in this next step we have changed this lambda, this variable lambda, by s. In the place of lambda I have written s. Then we get fx equal to 1 by 2 pi integral minus infinity to infinity e power minus isx integral minus infinity to infinity f of t e power ist dt ds. Now here this is nothing but 1 by 2 pi integral minus infinity to infinity e power minus isx into f of s ds. What is f of s? F of s is nothing but integral minus infinity to infinity f of t e power ist dt, which is called Fourier transform of the function f of x. And f of x equal to 1 by 2 pi integral minus infinity to infinity e power minus isx f of s ds is called inverse Fourier transform of f of s. Okay, so these are Fourier transform. These are the definitions of Fourier transform and inverse Fourier transform. Now here inverse Fourier transform, this represents a non-periodic signal fx in terms of continuous sum of exponents with frequencies between minus infinity to infinity. That means any non-periodic signal can be transformed from time domain to frequency domain using this inverse Fourier transform. Using Fourier series, we can convert from time domain to frequency domain, but only periodic signals can be transformed using Fourier series. Using Fourier series, we can change, or we can write any periodic signals into sum of sines and cosine terms. But using Fourier transform, we can convert even non-periodic signals from time domain to frequency domain. Now using Fourier transform, here Fourier transform is f of s equal to integral minus infinity to infinity f of t power ist dt. This gives amplitude of exponents at different values of s. This represents a continuous spectrum. In Fourier series, if a range L is extended up to infinity, then here frequencies are very densely packed. Then in frequency spectrum, we get a continuous spectrum. We have discussed this in our introduction of this unit. If we see this is Fourier in this signal. So in this signal, if you increase this range here t naught, here t naught, t naught, if you increase this range up to infinity, then we get a continuous spectrum in frequency domain. Okay, so here Fourier transform gives this continuous spectrum. Here in Fourier transform, if you increase this range in Fourier series, here you get a Fourier transform that gives continuous spectrum. Now, let us see applications of this Fourier transform. Here this is used in image processing and image filtering, image recognition, image compression, and it decomposes a signal into its constituent frequencies. Where Fourier transform decomposes a periodic as well as non-periodic signals into their constituent frequencies. But Fourier series can decompose only a periodic signal into its constituent frequencies. Okay, now let us see what is Fourier cosine transform. To define Fourier cosine transform, we use Fourier cosine integral. Here Fourier cosine integral is fx equal to 2 by pi integral 0 to infinity cos sx integral 0 to infinity f of t cos st dt ds. Now using this definition, we can write all t terms within one bracket. So if you write all t terms f of t cos st dt and the integral 0 to infinity within one bracket, that gives a Fourier cosine transform. So we can write this as fc of s, fs subscript c. This indicates Fourier cosine transform. So Fourier cosine transform is denoted by here fs subscript c or fc of s. Okay, so here fc of s is integral 0 to infinity f of t cos st dt, which is called Fourier cosine transform of f of x. Now f of x equal to 2 by pi integral 0 to infinity cos sx fc of s ds is called inverse Fourier cosine transform of fc of s. Now let us see Fourier sine transform. So to get Fourier sine transform, again we consider Fourier sine integral, which is fx equal to 2 by pi integral 0 to infinity sine sx integral 0 to infinity f of t sine st dt ds. So here also if you write all t terms within one bracket, this gives Fourier sine transform. So Fourier sine transform is denoted by fs subscript s or fs of s. So here fs of s equal to integral 0 to infinity f of t sine st dt, which is called Fourier sine transform of fx. Now fx equal to 2 by pi integral 0 to infinity sine sx fs of s ds is called inverse Fourier sine transform of fs of s. Now here I have listed some 5 examples on Fourier transform and 5 examples on Fourier cosine transform. Again some 4 examples on Fourier sine transform. So to solve all those problems, first let us see working method. In this working method, in first step you have to observe given function. If fx is given, if function is given, and if it is asked to find any transform, Fourier transform or Fourier sine transform or Fourier cosine transform, then we use respective formula to find those transforms and we evaluate that integral. So here to get Fourier transform we use this formula. To get Fourier cosine transform we have to use this. To get Fourier sine transform we have to use this formula. So according to given question we have to use any one of these 3 transforms. Now if you find any sub question within that question, that is after finding this Fourier transform, if you have to find or if you have to evaluate any value of any integral, then after getting that Fourier transform, using inverse Fourier transform, using formula of inverse Fourier transform of respective transform, we evaluate that integral. So to get or to evaluate the integral, we use any one of these 3 according to given question. So here inverse Fourier transform is this one, inverse Fourier cosine transform is this, inverse Fourier sine transform is this one. So to solve these questions means solving these questions is very simple. So using Fourier transform formula we find the transforms, and if you want to evaluate any integral then we use inverse Fourier transform to get that to get value of that integral. Now let us solve these questions one by one. First one is find Fourier transform of fx equal to 1 for mod x less than 1, 0 for mod x greater than 1. Hence evaluate integral 0 to infinity sin x by x dx. So here along with this for transform, it is asked to evaluate this integral. So first we have to find Fourier transform using Fourier transform formula. Then using inverse Fourier transform formula, we have to evaluate this integral. So first let us solve this question. Now, what is given function? Given function fx equal to 1 for mod x less than 1 and 0 for mod x greater than 1. This is the given question. Now, this function can be written as here 1 for minus 1 less than x less than 1 and 0 for minus infinity less than x less than minus 1 and 1 less than x less than infinity. That means here mod x is given. That means here 0, if you consider number line 1, 2, 3 so on, minus 1, minus 2 so on. In this interval, here value of fx is 1. And in this interval value of fx is 0. Here fx equal to 0. Here this is 1 to infinity, up to infinity. Here up to minus infinity. Okay, so here because mod x can be defined as mod x equal to x when x is greater than 0 minus x when x is less than 0. So according to this definition, here mod x less than 1 can be defined as x less than 1 and minus x less than 1. Minus x less than 1 means x greater than minus 1 implies minus 1 is less than x. Implies minus 1 is less than x. If you club this one and this one, you get minus 1 less than x less than 1. Okay, so we can write mod x less than 1 as minus 1 less than x less than 1. Okay, now after modifying these limits, so let us write definition of Fourier transform, because we have to find Fourier transform. So here Fourier transform is fs equal to f of fx, okay, equal to integral minus infinity to infinity f of x e power is x dx. In the definition, whatever we have seen, I have written this definition in terms of t, but here given function is in terms of x. That's why here we have used fx e power is x dx. Okay, is x dx. But what is this function? Here function is given in 3 intervals, minus 1 to 1, minus infinity to minus 1, again minus 1 to 1 and 1 to infinity. So here this can be written as integral minus infinity to infinity fx e power is x dx can be written as integral minus infinity to minus 1 fx e power is x dx plus integral minus 1 to 1 fx e power is x dx plus integral 1 to infinity fx e power is x dx. So in this interval minus infinity to infinity, value of fx is 0. So minus infinity to minus 1, 0 into e power is x dx plus integral minus 1 to 1, 1 into e power is x dx, because in the interval minus 1 to 1 value of this function is 1, plus integral 1 to infinity. Here in the interval 1 to infinity value is 0. So 0 into e power is x dx, which gives integral minus 1 to 1. Here fx is 1. So e power is x dx, because remaining 2 integrals they become 0. So we get only middle integral. Now if you integrate this using the formula e power ax, here integral e power ax dx equal to e power ax upon a. If you use this formula, if you use this, here we get e power is x upon is under the limits minus 1 to 1. Now whenever you apply limit, first we apply upper limit, so put x equal to 1. So e power is by is minus e power minus is by is. which is equal to e power is minus e power minus is upon is. So this is nothing but if you multiply and divide this by 2, you get 2 into e power is minus e power minus is upon here 2i, s into 2i. Okay, this is nothing but 2 by s, here e power is minus e power minus is upon 2i. This is 2 by s sin s, or you can write 2 into sin s upon s. This is Fourier transform of this function. Here, this is nothing but formula of sin s. Here, sin x equal to e power ix minus e power minus ix upon 2i. So, according to this formula, we have written e power is minus e power minus is upon 2i as sin s. So, here this is Fourier transform of given function. Now, we have to evaluate value of the integral. So, to evaluate the integral, what is that integral? Here, to evaluate integral sin s upon s ds, integral 0 to infinity, sin s upon s ds, or sin x, it is asked, sin x upon x dx. Here we use inverse Fourier transform, So here formula of inverse Fourier transform is fx equal to 1 by 2 pi integral minus infinity to infinity, here f of s e power minus isx ds. Here f of s we have seen, we have evaluated that Fourier transform 2 into sin s upon s. So we can write that here. So 1 by 2 pi integral minus infinity to infinity 2 sin s upon s into e power minus isx ds. Okay, now e power minus I theta can be written as cos theta minus I sin theta. So e power minus isx can be written as cos is minus cos sx minus I into sin sx. So we write 1 by 2 pi integral minus infinity to infinity. Here this 2 you can take outside. If this 2 you can take outside, these will get cancelled. So you can write only 1 by pi integral minus infinity to infinity sin s upon s cos sx minus I sin sx ds. Okay, now here cos sx is even and sin sx is odd. So this integral can be written as minus infinity to infinity sin s upon s cos sx dx minus 1 by pi integral minus infinity to infinity. Here I is there, we can take I outside. Here sin s by s into sin sx ds. Sin sx ds. Now since sin sx is odd function, this is odd, so this becomes 0 minus 0. Here since this is even function, we can write this as 2 by pi integral 0 to infinity sin s upon s cos sx ds according to definite integration formula. What we have seen, when we were discussing complex form of Fourier integral. What is that? Integral minus a to a fx dx equal to 2 integral 0 to a fx dx if fx is even, dx if fx is even, which is equal to 0 if fx is odd. So according to this, the second integral becomes 0, value of the second integral, and this first integral becomes 2 by pi integral 0 to infinity sine s by s cos s x dx. Now on left hand side fx is there. Okay, so let us put x equal to 0 in this integral. So here fx equal to, that is fx equal to 2 by pi integral 0 to infinity sine s upon s cos s x ds. Here put x equal to 0. Then we get f of 0 equal to 2 by pi integral 0 to infinity sin s by s into cos 0 ds. Value of cos 0 is 1, and here fx equal to 1 in the interval minus 1 less than x less than 1, 0 in the interval minus infinity less than x less than minus 1, and 1 less than x less than infinity. So here 0 lies between minus 1 and 1. Here 0, minus 1 plus 1. So here at 0 value of fx is 1. So here 1 equal to, here f of 0 equal to 1, since here 0 lies between minus 1 and 1. So 1 equal to 2 by pi, here value of cos 0 is also 1, we have written here. So here we get 2 by pi integral 0 to infinity sin s by s ds implies integral 0 to infinity sin s by s ds equal to 1 into 1 by 2 by pi, which is equal to pi by 2. So if you replace x by x, therefore integral 0 to infinity, if you replace s by x sin x by x dx equal to pi by 2, which is required integral. Next question is evaluate or find Fourier transform. Find Fourier transform of fx equal to 1 minus x square mod x less than or equal to 1, 0 for mod x greater than 1. Hence evaluate integral 0 to infinity x cos x minus sin x upon x cube into cos x by 2 dx. We have to evaluate this integral after finding Fourier transform. So here function is given. Function is fx equal to 1 minus x square. Here mod x less than or equal to 1 can be written as minus 1 less than or equal to x less than or equal to 1, and 0 for minus infinity less than x less than minus 1, and 1 less than x less than infinity. So we have seen this one, right? Means by here writing this limit in other way. Now let us write formula of Fourier transform. Fourier transform is fs, which is equal to f of fx equal to integral minus infinity to infinity f of x e power is x dx, which is equal to integral minus infinity to minus 1 f of x e power is x dx plus integral minus 1 to 1 fx into e power is x dx plus integral 1 to infinity fx into e power isx dx. If you observe, in the interval minus infinity to infinity, value of fx is 0. So this total integral becomes 0. Then in the interval minus 1 to 1, fx is 1 minus x square into e power isx dx. Again, in the interval 1 to infinity, value of the function is 0. So here we get only one integral, middle integral, which is equal to integral minus 1 to 1 minus x square into e power isx dx. Here to evaluate this integral, here we apply integral uv formula. So let us see that. Here integral uv equal to uv dash minus u1v double dash plus u2v triple dash minus so on. So here consider u equal to 1 minus x square, 1 minus x square, and v equal to e power isx. Now u1 means first derivative minus 2x, u2 equal to minus 2. Okay, and here v dash equal to integration e power isx upon is. Then v double dash means integration of v dash e power isx upon I square s square. Then v triple dash equal to e power isx upon I cube s cube. Okay. Now integral e power ax means integration of, how do you get this? Integral e power ax dx equal to e power ax upon a. Using this, here we got this integral. Okay. Now let us see this integral. What is that? Fx equal to, here integral minus 1 to 1, fx equal to, or fs equal to integral minus 1 to 1 minus x square into e power isx dx. Now according to this uv rule, first u, that means this one, 1 minus x square into v dash means e power isx upon is minus u1 means minus 2x into v double dash means this one, e power isx upon I square s square plus u2 means minus 2 into v triple dash, that is e power isx upon I cube s cube. Next term becomes 0 because derivative of minus 2 will be 0. So here limits are from minus 1 to 1. Now let us simplify this. 1 minus x square into e power isx upon is plus, minus into minus plus, 2x into e power isx upon I square means minus 1 into s square. Here minus 2 into e power isx upon I cube means minus I into s cube under the limits minus 1 to 1. Still we simplify this again. 1 minus x square into e power isx upon is. Here this minus sign we can take here, minus 2x e power isx upon s square, here plus 2 e power isx upon I into s cube under the limits minus 1 to 1. Now let us put upper limit first. Put x equal to plus 1. Then we get 1 minus 1 into e power is upon is minus 2 into e power is upon s square plus 2 into e power is upon I into s cube. Now when you apply lower limit, signs of these terms they will change. So minus of 1 minus 1, because minus 1 whole square is plus 1 only, e power minus is upon is plus 2 into minus 1 e power minus is upon s square minus 2 into e power minus is upon is cube. So let us simplify this. Here first term becomes 0. Here minus 2 into e power is upon s square. Here plus 2 into e power is upon is cube. Here again this term becomes 0. Here minus 2 into e power minus is upon s square. Here minus 2 into e power minus is upon is cube. Now we can write these s square and s cube terms together. If we write those s square and s cube terms together, here we get here minus 2 by s square, here also minus 2 by s square, right? Here 2 by is cube, here 2 by is cube. So if we write those, if we club those, you get which is equal to minus 2 by s square into e power is plus e power minus is. Here plus 2 by is cube e power is minus e power minus is. Let us check. Here if you take minus 2 by s square common, you get e power is plus e power minus is. If you take plus 2 by is cube common, you get e power is minus e power minus is. Now if you multiply and divide this by 2, here you get minus 4 by s square minus 4 by s square e power is plus e power minus is upon 2. I have multiplied and divided by 2. Here also, here 4 by s cube, 4 by s cube e power is minus e power minus is upon 2i. If you multiply and divide by 2, then this gives minus 4 by s square cos s plus 4 by s cube sin s. Here since e power x plus e power minus x by 2 equal to sin x. Okay, e power ix plus e power minus ix upon 2 equal to cos x, and e power ix minus e power minus ix upon 2i equal to sin x. So according to these definitions, here we have written, or we have converted these exponential terms into trigonometric terms using these definitions of circular function. Okay, now here therefore we can write fs equal to, therefore this is nothing but fs equal to this. Now we have to evaluate value of the integral. So here to get integral 0 to infinity x cos x minus sin x upon x cube into cos x by 2 dx. Consider inverse Fourier transform. Inverse Fourier transform fx equal to 1 by 2 pi integral minus infinity to infinity f of s e power minus is x ds. Now here this is f of s, so we substitute this f of s in this formula, then we get 1 by 2 pi integral minus infinity to infinity minus 4 by s square cos s plus 4 by s cube sin s into e power minus is x ds. This can be written as 1 by 2 pi integral minus infinity to infinity. Here minus 4, here minus 4 you can take outside. If you take minus 4 outside, here minus 4, this becomes, if you take LCM, s cos s minus sin s upon s cube into e power minus isx ds. Okay, now here put x equal to 1 by 2. Let us put x equal to 1 by 2. Now here you can cancel this minus 2 by pi. So let us write fx equal to minus 2 by pi integral minus infinity to infinity. Here s cos s minus sin s upon s cube into cos of isx e power minus isx ds, right? So here e power minus isx dx. Now put x equal to 1 by 2. Put x equal to 1 by 2, we get f of 1 by 2 equal to minus of 2 by pi into here this integral can be written as integral 0 to integral 0 to infinity here minus 2 by pi into here this one is 2 integral 0 to infinity here s cos s minus sin s upon s cube into here we get cos of 1 by 2 s by 2 ds. How do you get this cos s by 2? Here we get e power minus isx, or shall I write whole step before substituting x equal to 1 by 2. First let us write e power isx as cos sx minus I sin sx. Here minus 2 by pi integral minus infinity to infinity. We have seen this step, this type of simplification in our previous solution. S cube into e power minus isx can be written as cos sx minus I sin sx ds. Now you can write this integral as minus 2 by pi integral minus infinity to infinity s cos s minus sin s upon s cube into cos sx ds plus 2I by pi integral minus infinity to infinity s cos s minus sin s upon s cube into sin sx ds. Here this is odd function and this is even function. So here this can be written as according to definite integration formula 2 integral 0 to infinity s cos s minus sin s upon s cube into cos sx ds plus 0, because this function is odd. So according to definite integration formula value of this integral will be 0. Now this gives minus 4 by pi fx equal to minus 4 by pi integral 0 to infinity s cos s minus sin s upon s cube into cos sx ds. Now put x equal to 1 by 2 on both sides. Then you get f of 1 by 2 equal to here minus 4 by pi integral 0 to infinity s cos s minus sin s upon s cube into cos of s by 2 ds. Okay. Now here value of f of 1 by 2. We know here fx equal to, what is fx? Fx equal to 1 minus x square in the interval minus 1 less than x less than 1, right? So here 1 by 2 lies between minus 1 and plus 1. So f of 1 by 2 equal to 1 minus 1 by 2 whole square. That means 1 minus 1 by 4, which is equal to 3 by 4. So here we get 3 by 4 on left hand side equal to minus 4 by pi integral 0 to infinity. Here if you replace s by x, x cos x minus sin x upon x cube, sin x upon x cube into cos x by 2 dx. Now if you replace minus 4 by pi to left hand side, if you transpose this to left hand side, not replace, transpose minus 4 by pi to left hand side, then we get integral 0 to infinity x cos x minus sin x upon x cube into cos of x by 2 dx equal to 3 by 4 into pi by minus 4. Okay, that means which is equal to minus 3 pi by 16. Minus 3 pi by 16, which is required solution.